So today what we want to do is our second video on the Terrell-Penrose effect of physics, specifically special relativity. In the first video we showed some simulations of this effect, and today we want to follow up by showing you the mathematics behind those simulations. So just to review, the Terrell-Penrose effect is what happens when you look at an object which is moving very rapidly, which is to say at a speed that is a substantial fraction of the speed of light. And what we observe is that the shape is deformed. Okay? And what we want to do, again, is talk about the math behind those simulations. Okay, so let's get started. So what we want to do to begin with is to put a Cartesian coordinate system into place. So here's our Cartesian coordinate system. This is X. This is Y. We're going to imagine that the origin of this coordinate system is an observer. So here's our observer. And this observer is looking at a point source of light. Here's our point source of light. And this point source of light, let's say for the sake of argument, is proceeding this way with a constant velocity, v. We're going to call this v over here. And let's say at a certain time, which we will call Te for emit, this source emits a ray of light which eventually is observed by the observer. It's detected by the observer at a time t. So t is the time that the ray reaches the observer in the observer's own reference frame, the frame in which the observer is at rest. Okay? So the source started here, but light speed being finite, while the light is moving this way, the point source is continuing to move over here and ends up at this new position. Okay? And this new position is r. We're going to call that the position vector r. And that's at time t. So this is where the source ends up by the time the ray of light has reached the observer. Okay? And here's a vector for that. This is r of t over here. Let's move this guy over here so we can see it better. So we're going to put him right there. That's r of t. Okay? Now, what is this vector here? Well, this is the distance it moved in a time t minus t emit. That's what this vector is right here. And then over here, what is this vector? Well, it must involve c, since c is the speed of light, and it must involve the propagation time, which is t minus te. And then what about the direction? Well, we don't know the direction, so we're just going to encapsulate our lack of knowledge in the unit vector u hat. Okay? So that's the situation. We have the source, which at time te was here, so I'm going to call this r, the position vector r at te. And source moves eventually to r at t, and while it does so, the light ray proceeds to the origin where the observer is located. Okay? So that's the situation. Now let's draw an equation, write down an equation about this. Well, the equation is not difficult. We can write here that r of t, that's this, is equal to r at time te, which is this, plus this change, right? So I'm going to write the change here. The change is v, change in position to be exact, times the time it traveled, which is t minus t emit. Okay? But R of TE, we know what that is, so let's plug that in. So we have R of T, again, we just take that over, equal sign. But now what is R of TE? It's this thing over here. It's U hat, our unknown unit vector, times the speed of light, times the propagation time, T minus TE. That's this thing, but we need a negative sign, don't we, to account for the fact that the arrow right now is going this way and we want it the other way. So we're going to put this as a minus sign. That's this thing, so that thing became this. And now again, plus V times the propagation time, T minus TE. Okay? Very good. And so we're going to go one more step now and notice the following. This equation is not in a convenient form because we have this annoying unknown unit vector here. So what we want to do is move V to the other side of the equation and isolate this for a reason we will show in a moment. So we're going to start again with R of T. So that's this bit. And now we're going to move this guy over. So we're going to say minus V times T minus TE. And now that's equal to, so the V came over like from here to here, and now we're going to get this term, which is minus U hat C, the speed of light, times T minus TE. Great. So now what can we do? We can square this equation. We can take the dot product of each side of this equation with itself. That will cause this unit vector, which we don't know, to go away. It will also take this vector equation, which is actually 3 equations, and turn it into a scalar equation. So we get 2 rather nice simplifications out of this. So let's go ahead and do the squaring. Okay? So the first thing we're going to get is R squared. We're going to get R squared. R dotted into itself is just R squared. Okay? Now what happens when we dot this into itself? We're going to get plus, the minus sign goes away, we get plus V squared times T minus TE squared. So again, that's the velocity squared, magnitude. This is the propagation time squared. But then we also get a cross term, which is minus 2, this thing, which is minus 2 R dot V, the dot product of the radius vector with the velocity vector, that's this bit, times the propagation time T minus TE. And on the right side, what do we get? We get a nice simplification. Again, the minus sign goes away when we square. Unit vector goes away when we square it, and we just get C squared times T minus TE squared. Okay, so this equation is basically what we're looking for, but let's clean it up a little bit, shall we? So right here, this thing, let's give this a name. We're going to call this tau. Okay? And what is tau? Again, it's T minus TE. That's the propagation time. And it will simplify things because it shows up in 3 different places in this equation. So let's rewrite it that way. So we're going to get R squared plus V squared, tau squared minus 2R dot V quantity. Sorry, that's not right. Tau equals C squared tau squared. And then let's get everything on the same side of the equation. So I'm going to move everything to, let's see, which side do we want to move everything to? Let's move everything to the right. So I'm going to put a 0 out here. We're going to move all this stuff over here. So we're going to have 0 equals. Now note we have tau squared occurring in two terms. We have this term and this term. So this is going to be c squared minus v squared quantity tau squared. Okay, so that takes care of this term and this term. And now the next one, moving it over, so it's going to be plus 2r dot v tau. So that takes care of this term. And then finally we have minus r squared. So that is our equation for the propagation time tau. Okay, we are now ready to solve this equation for tau. So let's go ahead and do that. Okay, so what are we going to get? We're going to write this over here. We're going to get tau equals minus this thing. So it's going to be minus 2r dot v plus or minus the square root of this thing squared. So that's 4r dot v. Sorry, that's kind of clumsy. Let's try that again. R dot v squared minus 4 times c squared minus v squared. That's this bit here, and then this bit here, which is nothing more than minus r squared. And that whole thing is under the square root, and then this all is divided by 2 times this coefficient, so that's 2 times c squared minus v squared. Okay, now let's do some simplifications, shall we? The first thing we notice is that we have a 2 here and a 2 here, they cancel, and the 2 here also cancels these 4s, so let's get rid of all that. So we're going to go here and get rid of this guy and this guy, this guy, and this guy, and finally this guy. Okay, good. Okay, next we notice that we have some signs to deal with. We have a minus sign here which cancels this. So let's change that. So we're going to get this guy and just make him go away. And then this other guy we're going to change to a plus sign. So that's one thing we can do right off the bat. Another thing we can do, just because it's convenient, is to work in natural units. In natural units, the speed of light is equal to 1, and the velocity is always less than 1. So let's do that. That will make life a little bit easier for us. I'm going to take this guy, this c squared, and just put a 1 in its place. And then also over here, we take this c squared and again put a 1 in its place. That just makes the equations a little bit easier to deal with. Finally, let's talk about this r dot v thing. So r dot v, so remember what this is. This is the position evaluated at detection time dotted into the velocity, which is constant, okay? But we could write this a different way if we wanted. We could write this as v. I'm going to change the order. Its dot product is commutative, so we say this is v dot, I'm going to write this in a parentheses. This is r times r hat, a unit vector, okay? And this is equal to r times v dot r hat, okay? But so think about what this is. This is the component of velocity in the direction of the unit vector in the direction of r. So it's really the radial velocity. So we can actually write this as r times r dot. That's just a little bit easier to carry around. So why don't we make that change as well? So I'm going to go up here and change this r dot v to r dot. Then I'm going to do the same thing over here. So this whole thing becomes, let's get this all erased. This becomes r squared r dot squared. So there's a couple of nice little simplifications to make our life easier. Last but not least, this thing down here, remember what that is. 1 over 1 minus v squared is actually the constant that is often used in special relativity, gamma squared. So let's do that as well. So now we're going to go up here, and we're going to get rid of this whole thing, because it's not necessary. We're also going to get rid of this and this. We're going to put parentheses around this whole thing and just write this as gamma squared, okay? How's that? Okay, now let's think about which sign is correct. Let's pay attention to some signs here, okay? Remember, tau must always be positive. It has to be greater than 0 because detection must always follow emission. We can never have a situation where detection comes before emission. So we know very well that tau must be positive. So we don't know what this term is going to do, but we do have some control here. And what we observe is that we can never have this negative sign. So let's just immediately we're always going to take the positive square root here. So let's make that change. So this guy just oops, I blew it. That just goes away, okay? Very good. That's point number 1. Point number 2, let's talk about factors of r. We've got an r squared in here under the square root, so effectively it's an r. Same thing here, r squared. So we can factor this whole thing and put an r in front of here, but we also have an r here. So what we can really do is get rid of this r, and we're going to get rid of this r squared, and we're going to get rid of this whole thing, and we're going to replace that with an r out here. I'll just put it over here for the time being. So that's another nice simplification. And when we're done, let's write this a little bit more cleanly now. So what we now have is tau. Let's write this right here. How about that? Tau equals, let's write the square root for, let's put this stuff out front. We've got a gamma squared r, gamma squared r. I'm going to put the square root first now, so it's going to be gamma squared r. I'm going to put this there. Now we've got this thing, which is square root of r dot squared plus 1 minus v squared. Very good. And then we have minus r dot. So there's a rather simple expression, more or less the way we want it now, for the propagation time tau. Okay, so we have the equation that we want. Now let's look at it a little bit and do some checks. So I'm going to scroll this up, and let's just see what we can see with this equation. So let's start by considering this square root. What we see is that we have a 1 here, so positive. R dot squared is positive, and v squared is always less than 1. So this argument is guaranteed to be positive. So there's no possibility of a complex tau. So that's a good sign. Next, if we look at dimensions, we notice the following. Let's just draw this like this. Okay, this whole thing is dimensionless. It's unitless, because in natural units where the speed of light is 1, all of these velocities are dimensionless. They're unitless. So that's a simplifying fact. The same applies to this gamma squared, because gamma is just involving a velocity, so it's also dimensionless. All we have is this tau and this r, and everything else is dimensionless. But in natural units, once again, time, that is to say, time and length have the same dimension. So this equation does indeed satisfy dimensional checks. So that's a good sign. So now let's get rid of all this extra stuff that we don't need. And let's go to another point. Let's see what happens in the case, this is a check now. Let's take the case where v equals 0, where the velocity equals, sorry, I'm making a mess of this. V equals 0 case. Let's think about that. In the v equals 0 case, both r dot and v are 0. So all that's left is the 1. So this whole thing just collapses to 1. This r dot, this whole thing is just 0. And gamma squared, because it involves a v, is just 1. So this whole thing is 1. So the whole thing just boils down to tau equals r, which makes perfect sense. The time for the light ray to reach the observer is exactly equal to r, or in the case where c is present, you would say r divided by c. You know, if we wanted to put the units back, we could say this, but you get the idea. So it appears that our equation satisfies the various checks that one might want to carry out on it. Hello, hello. Okay, so at this point, you might be asking yourself, what is this equation good for? Well, with this equation, whoops, that's not right. You can simulate a single point source. And how do you do that? So with this equation, you can simulate a single point source. What do? You specify two things. You specify the velocity vector of the object in question, and you specify its position vector at a given time. So this is at some arbitrary time. Okay? From there, you can calculate V R, it's known by, and R dot. And once you do that, you can calculate tau from this equation, and from that, you can get the apparent position of the source. So that is what you can do. And to be clear, what you do is you simply take the R apparent, which is actually R emit, so I'm going to use an E. The apparent position is equal to R, the value that you input over here, this guy, and say minus V, which you know, tau. That's the equation for the apparent position. So with these two equations, you have everything you need to handle a single point source of light. So this, I'm just going to say, this handles a single point source. Okay? But as we've said, that's not a very interesting case. However, you can have more than one point source. Okay? You can make something fancier. Let's think about that. Let's say you wanted to look at the apparent shape of a circular object. Well, instead of a single point source, you might make something like this. Okay? And then follow that same calculation for all of these. However, so this is the case of multiple point sources. Okay? But the thing is, we actually are not quite ready to do this case yet, because as soon as you add another point source, you have to take another physical effect into account, and that is the Lorentz contraction. So that's an important thing that we haven't addressed yet. And the reason we didn't address it is that because you can't Lorentz contract a point source. It's already a point. It doesn't get any smaller than that. But as soon as we have two, we have to think about the Lorentz contraction between them. So let's remind ourselves how Lorentz contraction works. The equation of interest just says the following. It says that the length of an object is given by, the length of a moving object is given by its length at rest, L0, times the square root of 1 minus v squared in natural units, where c is equal to 1. We could also write this, if we prefer, as L0 over gamma. And that's the other piece of the puzzle. So between this equation, whichever one you like best, and this equation here, you have everything you need to construct a simulation. Okay, so we're now ready to think about what experiment we want to do. That is to say, what experiment we want to simulate. So let's discuss the experiment. Okay? The experiment is actually rather simple. Okay? Step 1 of the experiment is construct an object. Construct the object of interest. Okay? We then accelerate the object. So at this point, its velocity is 0 relative to the observer. Now we want to accelerate the object and bring it up to a final speed v, which is not equal to 0 now, okay? Not equal to 0, okay? And then, once we've accelerated it, we want to observe it. Observe it. That's really all there is to the experiment. Okay, so now let's say we want to construct a simulation of that experiment. How do we do this? Well, what we do is the following. Simulation. Okay? Now, what is the analog of constructing an object? What we have to do is we have to assign positions to the point sources. Okay? That's what constructing an object means in simulation land. Next, what's the analog of acceleration? Well, what it is, just to be clear that there's no confusion here, we accelerate the object to a final constant velocity. And that constant velocity, once it reaches that constant velocity, the acceleration ends and there is no acceleration any further. So what we do is we apply Lorentz contraction to all of these positions, to all of these guys. And then what is the analog in mathematics or computation to observing? Well, it's simply apply the equation for what we've called latency, or equivalently the propagation time. Propagation time. Okay? That's the basic idea of the simulation. We now have a vague idea of what we want to do with our simulation, and it lines up fairly closely with the experiment itself. In the real life, we construct an object, and in simulation world, what we do is we assign positions to the point sources of light which we are using to represent that object. So there's a correspondence there. Then in real life, we accelerate it to some constant non-zero velocity, whereas what we do in the simulation is apply a Lorentz contraction. Finally, in real life, we observe it. We take a picture of it with a camera, or we look at it with our eye or with a telescope. While in the simulation, we apply the latency equation to get the propagation time, and from that we can get the apparent position of each point source. Okay? So let's plunge into this now and go into this in a little bit more detail. So let's just write here simulation details. So there's a little bit more detailed view of what we want to do. Okay? So First thing, of course, is to specify the position of, we want to specify, so I'm just going to say set R. What is R? It's the position of the object. It's the position of the object of interest, okay? And more specifically, it's actually the centroid in the way we are doing it. You could do it other ways, but we chose the centroid, okay? And that's, just to be clear, it's at the time of observation. So it's the true position. Let's write that here. It's the true position of the object at the time of observation, which is arbitrary. Okay? So that's point number one. Point number two, we have to specify a velocity, v. And remember that velocity, and this is a number, just to be clear, it's a number between 0 and 1 because we're in natural units, okay? And we're going to assume that this is totally in the x direction, okay? There's no loss of generality. That just makes life a little bit easier for us mathematically, okay? All right, once we have those two things behind us, the next thing to do is to build the object. And what we do is we specify or set delta r sub I. So this is the position of the ith source, the ith point source relative. Let's put here relative. Ith point source. Let's do that even differently yet. Relative to the centroid, which we specified earlier. Okay? So we do that, and so this is done for I equals 1 up to n, the total number of sources, okay? Very good. Once we have that, we can now apply Lorentz contraction, okay? And the way we do that is the following. We say, because the thing's moving only in x, only the x coordinate of these delta r sub i's is affected. So we say delta x sub I with a subscript c for contracted equals delta x sub I divided by gamma, which we defined earlier, the famous gamma factor. Okay? We have now Lorentz contracted our object. We just put these delta x's in place of the delta x's that we had in here, the x components that we had in here before. Okay? Now we can get the actual absolute positions of these things in the frame, the reference frame of the observer. And we'll say r sub I, the position of the ith component, ith source rather, is equal to r, this thing up here, plus delta r sub I subscript c for contracted. So remember, we changed the x components of these things, and they became the contracted coordinates. So now we have the absolute position of each point source, and we know its velocity. We're now in a position to compute. We can now compute using our latency equation, tau sub I. Again, I equals 1 up to n. And then from that, we can compute using the equation of motion. Let's write it this way. R sub I, the position of each source. But now what we're interested in is the emit point, because that's the absolute, sorry, that's the apparent position. The emit point is the apparent position, is equal to, let's just get this correct here. It's r sub I, it's this thing, r sub I c, this thing right here, minus velocity times tau. Okay, so now let's be really clear about something here. This is not a, it looks a little bit like an E, but it's not. It's a C. It's this thing here, the contracted position, okay? So that's the true contracted position of the ith point source at the time it is observed, which is to say at the time the ray of light from this thing, this particular point source, reaches the observer, okay? And then here we have the velocity vector, and this is tau, but this is not any tau, this is tau sub I. And it's worth emphasizing that every point source in general has a different tau. That's how we assure that all of the rays of light converge to the observer at the exact same instant of time. Okay? Very good. So now we have the thing we wanted. This is the result we were after. It's the emit position for each point source at a given time. And with that, we can now draw the object. We can render it. We can render, that's the next step, is to render the object. Render the object. And this can be done in a lot of different ways. I use Mathematica, and in Mathematica there's a function called graphics 3D. Graphics 3D. It's a function in Mathematica that you can use to render this object. And so with this method that we've just outlined, you can simulate the apparent shape of any object that you care to. You simply create a collection of point sources that has the shape of interest, and the rest shape of interest, shall we say. And once you've done that, you, in simulation land, accelerate it to a new constant velocity that's a substantial fraction of the speed of light, and you render it and you can see what it would look like. So we will stop there for now. In the next video, we will talk about some of the ramifications, observations, and conclusions, and so on.